So in the first half, we talked about polyethylene polymerization, some of the properties of polyethylene. Now we're going to talk about how you choose a polyethylene resin for an application. And the resin choice, honestly, for everything, not just polyethylene, is based on important properties like density, melt index, and molecular weight distribution of the resin. Density is kind of determined by pressure. So there are three general density categories of polyethylene: low, medium, and high. And these are the ranges that define low, medium, and high. And the ASTM classifies these into different groups. So low density polyethylene falls into group 1, medium falls into group 2, most high density polyethylene falls into group 3, and then the really, really crystalline stuff falls into group 4. And melt index is another important parameter. Now, the definition of melt index is the amount of polymer that can be extruded through a melt indexer. And the typical parameters are how much polymer, in terms of grams, can pass through a fixed orifice in 10 minutes at 190 Celsius and a specified pressure. That is how you measure melt index. So it's grams per 10 minutes are the units that you have on melt index. So when you have a higher melt index, you have lower molecular weight, lower melt viscosity. It represents something with lower tensile strength, lower softening temperature, and lower toughness. A lower melt index means higher molecular weight, higher melt viscosity, better impact resistance, better stress cracking resistance, but it's not as easy to process. So there's a trade-off based on melt index. But this is the definition of melt index. You will likely be asked to tell me what that is, along with dissipation factor. When it comes to molecular weight distribution, that is important as well. A narrow molecular weight distribution tends to give better low temperature properties and higher impact strength. A wider molecular weight distribution is good for ease of processing. It starts to soften and melt at lower temperatures. And once again, how do we determine molecular weight distribution? Well, that is your polydispersity index. So your weight average molecular weight divided by your number average molecular weight. For your typical synthetic polymer, your PDI, polydispersity index, is 1.5 to 2.5. So as you increase your polydispersity index, in other words, you widen your molecular weight distribution, you get a decrease in toughness, a decrease in softening temperature, an increase in brittleness, and an increase in susceptibility to stress cracking. So when it comes to the applications for polyethylene, you're looking at a lot of blown film. 60% of all polyethylene is used in blown film. Most polyethylene types are used in blown film products, anywhere from 0.9 to 0.964, depending on the manufacturing process. The property requirements for blown films is that they have high tear and impact resistance, high gloss, and low haze. So what you're looking for in something that's used for blown films in terms of high density, you're looking at a melt index of 0.01 to 2 grams per 10 minutes, and low density polyethylene you're looking at 0.4 to 6 grams per 10 minutes. LDP films tend to be clearer and more flexible than high density polyethylene films. That's a direct result of the crystallinity. Crystallinity equals brittleness. Brittleness is the enemy of flexibility. So lower density polyethylene films have lower crystallinity and are more flexible. I will never not say this. Anything of the polymer structure directly impacts properties, some more directly than others, but in this case, the flexibility of your bag goes back to the crystallinity on the molecular level. When it comes to blown films, these include a wide variety of things: general purpose packaging, lamination, frozen food bags, ice bags, shopping bags. If you've never seen a blown film line, it's actually pretty cool. I mean, I'm a chemist, so anything on the processing end is really cool to me. I just kind of stand there and go, ooh, ah, kind of like I'm watching fireworks. But this is a blown film line. This is attached to extruders, and then the die is pointed upward. And blown film lines can be a couple stories in height. So this is one of those examples. If I find a good video, I'll also upload it. Apparently this picture was taken in the 70s, but you get the idea. Lots of food packaging made from blown films. Cast films are not blown films. Cast films have higher gloss and clarity than blown films. Casting of these films is often done on a high-speed chill roller, and basically the material is cast onto a roller and it's run very, very fast. And so the speed implies rapid cooling, and then it quenches it. That's how you get the clarity out of a semi-crystalline polymers through that quenching. So again, this is anything from low density to high density, and the melt index for this tends to be a little higher. When you're shock cooling it like that on a chill roller, you're getting increased gloss, smoothness, and optical properties. In this case, the optical property you're looking for is clarity. And these are for bread bags, frozen food bags, general purpose packaging, and diaper linings for cast film polyethylene. Here are some examples of this. It can be dry compounded or co-extruded, and includes food all the way up to medical flexible packaging. Also, you have construction film up to 10 feet wide and 100 feet in length on a roll. This also can be extrusion coating and laminating. A lot of paper products are laminated with polyethylene. If you ever get a chance to visit Chevron Phillips, they sell a lot of polyethylene, and they have all of the equipment that would be necessary to process the polyethylene, so they can do blown film, cast film, extrusion coating, and laminating. So every now and then we do a Focus on Films workshop there, and I know it educated me quite a bit on what all these things were. Extrusion coating and laminated products are a little bit higher in the density range, and their melt index tends to run a little bit higher. The desirable properties for something for extrusion coating is a good draw property, so film sheet orientation and then thickness reduction versus applied force. You want minimum pinholes, so you want a nice, smooth, even coating across. It's true for any coating, really. And minimum odor and taste transfer. So you want so pinholes would allow odor and taste to go through. You want to minimize that. You enhance the barrier properties by increasing a moisture barrier, a grease barrier, a heat seal layer. So if you line a bag with this, you can heat seal that polyethylene to get it to close, like in a chip bag. And you can also create a tie layer in laminates. These include coating and laminating of milk and food carton stock. This is the highest volume. Lining of craft paper, so that brown paper. Foil and polymeric films for like chip bags. Spiral wound cans for motor oil, fruit juices, the biscuits that explode on you at the moment's notice, and also an adhesive layer in snack food packages. Polyethylene is also blow molded. This again is over most ranges of it. When you're looking at HDPE, you're looking at the lower range of melt index. You get good stiffness, toughness, and load capacity, low temperature properties. Anything that's blow molded is something with a hollow interior. So bottles are the typical thing. Milk, bleach, detergent, personal care products. Personal care products tend to be low density polyethylene because you want it to be squeezable. Lots of toys, ice chests are blow molded. Some of the ducts for automotive air conditioning and heating, under the hood reservoirs for tanks. Some of those are roto-molded, but some of them are also blow molded. Carrying cases for power tools, and then industrial drums or gasoline tanks. In this case, the very high molecular weight material is used for those particular applications. So here's some examples of blow molded bottles. So these are ampules used in medical applications, your typical consumer bottle, and then we have some cases and ice chests, things like that. Injection molding is also big for polyethylene products, and it's very suitable for parts that require rapid production, detailed finishes. Your melt index can range anywhere from 1 to 100, and you can get a really wide range of properties because they are so versatile. Apparently chicken crates are an important application, so I'll mention those. Tote bins, food containers, dairy products, cups, frisbees, you name it. This is an injection molded product made out of polyethylene, and this is a micro injection. This is the tip of a pencil, and this is for a vascular connector. So if you're going to, people who have to do dialysis, often they need vascular connectors, and this is one way they go about doing that. So this is 0.008 inches or 200 microns in the average wall thickness. This is very, very small, and this is one application of injection molding of a commodity polymer for biomedical applications. Extruded products are also made with polyethylene, pipes, other things for profile, both low density and high density. High density is dominant because of the toughness and the abrasion resistance and the creep resistance. So you're looking at on the higher range of density. Melt index ranges fairly widely. So drinking water pipes, corrosive chemicals, irrigation, sewer lines, gas distribution, flexible tubing for medical purposes, and oil and gas gathering lines. This is a manhole made out of polyethylene. So this is a large profile product that is extruded but made entirely out of polyethylene as opposed to steel. This is a extruded pipe for a city sewer line. These are flexible, very cost effective. They can withstand a lot more vibration resistance than traditional metal pipes, and they're a lot easier to install. PEX is a little bit different. When you talk about PEX piping for homes, that is cross-linked polyethylene, but that piping for homes is also superior to, say, copper or especially the old cast iron pipes. Polyvinyl chloride has a few more, it has a lot of application as well, but PEX is very flexible. So piping made out of HDPE or cross-linked polyethylene is getting a lot more attention for household piping as well. This is waterline piping. One of the things for this is that this has really good corrosion resistance and flexibility. Polyethylene is very cost effective because it costs so little per pound. So this is one of the reasons why for piping, especially for municipal or industrial purposes, is advantageous. Also, dual containment pipeline. If you are piping something that is corrosive or nasty in this particular one and somehow this pipe fails, if you do not have anything between this pipe and, say, a water supply or your shop floor or whatever, that can be an environmental hazard. So they also make these dual containment pipes. So this is one pipe that's fitted outside this inner pipe. So there's something nasty going through here, and this contains it if there's some sort of spill. Typically you'll see a reduction in pressure that indicates a failure of the inner pipe, and then you can deal with it before it's an environmental hazard. Again, polyethylene is used for wire and cable coating, and it is co-extruded in order to do that. So you have your wire cable coat product, here's your wire itself, you have your crosshead die, and that kind of covers all of this, and it comes out here. So extruder, cable, they come together, and then you get your coated wire at the end. Polyethylene is made into sheets for thermoforming. This is often done for the mid-range to lower-end truck bed liners, the mini swimming pools, the ones that my dogs cavort in over the summer, food containers, and shipping containers. Thermoforming for food containers and shipping containers is huge. Sometimes it's done with polyethylene terephthalate for clarity, but polyethylene is often used. It's translucent enough that it produces good food packaging, especially for food containers. Polyethylene is also almost exclusively used for rotomolding. The polyethylene doesn't come in pellets. It is ground up into powder for good heat transfer, sugar-like or smaller in terms of the particle size. You need a relatively narrow melt index range, so 5 to 8. This is not truly thermoplastic. Typically there are additional peroxides added to this to get it to lightly cross-link during processing so that it has better impact properties. And the typical application areas for rotomolding are chemical tanks, water tanks, and trash containers. And these can be huge. So huge that several people can stand inside one of these rotomolded tanks. Polyethylene is also co-extruded, so you can create films with multiple layers. And this is an example. So you have polyethylene terephthalate, an adhesive layer, EVOH, another adhesive layer, and PET, and they're all kind of co-extruded, and then the multi-layer composite laminate comes out. This adhesive layer is typically polyethylene. It's used for a tie layer. Polyethylene has good moisture barrier properties. It seals things together very well. It tends to melt at a lower temperature than the other layers you are co-extruding, so it flows really well and sticks things together. So this is an example. So you have polyethylene, medium density polyethylene on the outside here, you have polypropylene in the middle, and then here's a food pouch where it's paper, polyethylene, aluminum foil, and a polyvinyl product there. So it's very good for co-extrusion. This is for food packaging, cosmetic packaging, pharmaceutical packaging, anything that requires kind of a barrier, but still flexibility and clarity and ability to decorate it, all that great stuff. Polyethylene is used exclusively for these environmental protection materials. And what this means is this is the liner that they put at the bottom of a landfill. So it prevents seepage. So all the nasty stuff that comes out from your garbage in liquid form, these are barriers to prevent that from getting into the groundwater. So again, good barrier properties, good tear strength, puncture resistance, and chemical resistance are the advantageous things about polyethylene that make it good for that application. This just shows that puncture resistance is better than PVC, tensile strength is higher, tear resistance is higher, so that just kind of gives them a bar graph of properties. I'm not going to spend too much time on this, but for your information, here are some general processing conditions for polyethylene. Again, if you really want to know, I suggest you ask Professor Herring. I could have easily done something wrong in this table, but this is just kind of for your reference. So that concludes polyethylene portion of polyolefins. After this, we'll move on to polypropylene. Thank you.